Hey level 3s, and welcome back to 3.4 atomic structure, bonding and thermodynamics. This is lesson 4, and our learning objective for this lesson is to complete Hess's law calculations using the sum of the products of formation, subtracting the sum of formation of reactants. So we're just going to get started. So we learnt last lesson about method 1 for Hess's law, which was the manipulation of equations. This one is much more straightforward, but there is a criteria. Okay, to do this reaction, all of the data must be given to you as formation data. Now, formation data, just to recap what the definition of formation is, enthalpy of formation is the energy released or absorbed when 1 mole of a substance is made from its constituent elements under standard conditions. So you do need to get those definitions sorted, and so they all have to be formation. So if you see in the question lots of little f's and only little f's, you think whippy, because yippee, because you get to do this equation here, sum of the products minus sum of the reactants. It's nice and easy. Just a wee note, this bit here, elements do not have enthalpy of formation data, and that's because they're in their natural state, and so there's no energy associated with that. So for instance, the enthalpy of formation of O2 is 0 because O2 is the elemental form. So the enthalpy of formation of carbon would be 0 because it's the elemental form. The enthalpy formation of H2, 0, as it's the elemental form, and so on. Okay, so let's have a look at an example. So here's a question. It says calculate the enthalpy of reaction for the esterification of ethanol with ethanoic acid using the information below. So what you can actually see is that, I know the bottom one, sorry, is a little bit cut off. I'll try and move the screen, is the fact that all of the data given to you is all formation, all little f's. So we go, woohoo, we can do this. So what we have to do here is we add up the sum of the products and subtract them off the sum of the reactants. Now, please, when you do this, one really good thing you can do for your marker in the exams is give a total. If you can total up the energy for the products and total up the energy for the reactants, and you get one of those correct, some years that actually gives you a merit. So that's a really useful thing to do. So let's get on with it. So the products is the ester, so negative 481 plus water, which is negative 286. Please be very mindful of states, and I've just realized here I should have put states, so that wasn't very good of me. So this here is liquid, this one's liquid, this one's liquid, and this one's liquid, and so you can use these straight away. But one way they try to do a little trick, sometimes, it's only if they're being really mean, is sometimes they'll give the thing here as being gas, and that's just to trip you up a little bit. It's not that common. Okay, so we add up these two to get an answer. Then we need to add up the reactants, which is going to be negative 487 plus negative 287, and then we subtract products from reactants. And I'll go to the next slide because I don't know the numbers off by heart. So here's the sum of my products. Okay, here's the sum of my reactants. I'm making it really clear to the marker. This is how I recommend setting out your answers. And so the answer is positive 7.00 kilojoules per mole. Please note your answer must be to 3 significant figures or you will not get excellence. 1 significant figure, 2, 3. Remember, zeros count after a number. Okay. So here's another example. Calculate the enthalpy of combustion of ethanol when given the following information. So you've been given all F's, so you go whoopee, because this means that, I keep saying whippy, what the hell is that? Yippee, okay, yippee, because you get to do sum of products minus sum of reactants. This one is a little bit harder than the last example, because the last example was a 1-to-1-to-1 stoichiometric relationship, but this one is a 1-to-3 to 2 to 3. So if you make 3 waters, then you need to times the enthalpy of formation by 3. If you make 2 carbon dioxides, you must times that by 2. This one also has an element in it, which we know is 0, so we just ignore it. So if we are adding up the sum of the products, we need to do 2 times the carbon dioxide, so 2 times negative 3 times 4, and add that to 3 times negative 286 and get our total. And there'll only be one reactant here because the oxygen's an element, which means that there's no formation data, it is just 0. So if we try this, okay, we add up the sum of the products, remembering to times by 2 and 3, just one reactant, making sure we separate these as separate calculations, and then we subtract products from reactants. Please include this equation in your answer. Okay, that gets you actually an achieved if you actually can show what you should have been doing, and that gives you the answer negative 1368 kilojoules. Now this is actually pretty bad of me, because it's 4 significant figures. But what's really interesting is if they give you an answer, a question like this, weirdly they'll accept 4 significant figures if you're already in kilojoules. Don't ask me why, but they will. Okay, so this is the one time where you can do 4 significant figures, or please feel free to turn it into 3 significant figures if you want to. Okay, let's do another example. Calculate the enthalpy change for the following reaction. Again, all formation, so yay. So we look at our equation. Oh, there's an element here, so we know we're not going to include that. So the products are going to be 2 waters, so 2 times negative 285. The reactant is going to be 297 and 2 times 20, negative 20, sorry. And we do products minus reactants. Okay, so we add up the sum of the products, the sum of the reactants, remembering to times this one by 2, and then we do the final products minus reactants here, and we get our answer into 3 sig fig wherever possible, which you should actually do every time, so you just never make a mistake actually. Okay, that is it. That is the whole lesson, and all you have to do is kind of practice. So there is a wee kind of what do we need to remember from this, okay? There are 2 main things. When you're given lots of different forms of equations, so combustion, formation, everything, then you know you need to do the manipulation method, which we did last lesson. When all the data is formation, you get to do the sum of the products minus the sum of the reactants. Remember, all of the units for this topic are kilojoules per mole. I'm not going to get into why it's not technically correct, but for NCA, it's all kilojoules per mole. So please make sure that you actually are doing that. If an answer is in joules, you need to convert it to kilojoules first, so you can calculate all of your different enthalpies. And that is it for today. And then we move, here's a super hard task, which I'd like you to pause your screen and give a go for. So pause your screen and give a go at this, and I'll flick through the answer. Just very quickly, some pointers to note here. You can see you've got both combustion and formation, which means you are doing method 1, the manipulation method. No equations are given to you, so you'll need to write the equations. Okay, so if you write the equations out, this is the combustion. A reminder that combustion means to burn 1 mole of a substance in oxygen to produce carbon dioxide and water, remembering the water is in the liquid state. Okay, the next one was formation. That's to make 1 mole from its constituent elements under standard conditions. This circle means standard conditions, so you always have to include that at the end of your definition. This next one is the formation of carbon dioxide, so making 1 mole from its constituent elements and making 1 mole of water. So here are the equations that you need to do. Okay, the next thing that you'll need to do is there's your desired equation, it was given to you. You need to work out what you need to do to each equation. Now remember what I said to you previously, that sometimes we just leave certain things to cancel themselves out, and today I'd highly recommend leaving oxygen. It'll sort itself out. So from equation 1, the only equation where this is in is this one, and we don't need to do anything. We want 1 mole and we want it as a reactant, so we're going to leave that. To equation 2, you can see that we need the ethanol. We need it as a product, but we need 2 of them, so we're going to times that one by 2. Okay, and I've done that here. To the next equation here, this is a little bit tricky, and the reason why it's a little bit tricky is because you actually have to look at 3 and 4 kind of together now. With equation 3, we want 2 CO2s as a product, and the reason why this is such a hard example is because if you look at all of your equations, CO2 comes up actually in two equations. It comes up in equation 1 and it comes up in equation 3, which means we're actually using equation 3 to actually get rid of 4 of the carbon dioxides in equation 1, which we don't need because we want 2 in our final equation, but equation 1 we have to leave. So we can't do anything to equation 1, and we've now stuck with 6 CO2s, but we only want 2 of them. So we need to use this equation 3 to cancel out 4 of them. Because equation 3 has it as a product and equation 1 has it as a product, we have to get those CO2s as a reactant, so we have to reverse it, and we need to times it by 4 so we can cancel out those CO2s. So the whole point of equation 3 is actually as a cancelling tool within our manipulations. So we need to times equation 3 by 4 and reverse it, which you can see I've done. The same thing has happened with equation 4. With equation 4, it's actually purely being used to balance out the problem that we're doing. It's not in our desired equation. We've got no water in our desired equation. But what you will see is equation 1, which again, we couldn't do anything to, we just had to leave, has got 6 waters. We don't want any waters in our final equation. The waters in equation 1 are a product, so that means that we need to make the waters in equation 4 a reactant so they can cancel. So we're going to reverse it, and then we need to times it by 6 so we can cancel out those waters. So hopefully that makes sense. Once you've done that, you can add them all together, cancel out species common to each side, and you'll realize that you've got your desired equation. So from then, we just add up all of those energies, making sure we've accounted for our manipulations, and we record it to 3 significant figures. Hopefully that makes sense. Any questions, let me know. Okay, team, so that's it for this lesson. If you've got any questions, jump on Teams, but I'm just going to let you know the whole thing here is practice, practice, practice. In today's lesson, you'll be doing some questions from a worksheet, which I've specified on the OneNote plan, and tomorrow's lesson, we're going to be doing Study Guide 10C. So we've actually got another lesson just consolidating Hess's law. Okay, team, thank you very much.